morning. To those of you who don't actually know me, my name is Jalen Phillips, and I decided to do my presentation today on denumerable sets. So, the background and motivation for this is a denumerable set is a set with a bijective relationship to the set of natural numbers, meaning it can be one-to-one compared all the way down. George Cantor was actually the father of set theory, and he proved the existence of denumerable sets in the process of proving that real numbers aren't countable. He was very into, along with several of his peers back in the day, studies of continuity and the continuum, and he built the set of real numbers as a response to the idea that infinity in a continuous set is like theoretical, not mathematically provable. So he effectively proved that a line is made out of infinitely many points, and that was then like made up numbers for that. In a letter with a friend of his, Denumerable, at the time, another mathematician was, saying, "Yeah, that sounds pretty cool. Do you think that set's countable?" And he said no, but it took him a few tries to prove it. So what we're going to look at today is actually his third time. He proved it twice before this, but this is the one he's most famous for and the one that I thought was most visually interesting. So the theorem behind his proof is that the unit interval 0 to 1 is not countable. And the reason he used this is because 0 to 1 has the same cardinality as the set of real numbers. So this is a table expressing a function, any function, from n to the interval 0 to 1, with decimal expansions through that function of all of the natural numbers, right? This obviously goes out infinitely this way and this way. So his proof, or his theory behind this, is that there are infinitely many numbers in this, or that don't appear in this table, that are between 0 and 1. He did this by lining things up diagonally. This is why it's called Cantor's diagonalization argument. So what he does is say any of these numbers, so f of 1, right, infinite definite, hello, can you come back over here? Okay, thank you. Infinite decimal expansion this way. You take at least one number from each row, and at most one number from each column. And you go down in that manner. So the ones he has highlighted here, 0.37210. You can add 1 to those, and you get 0.48321, right? This is still obviously between 0 and 1. However, this number can never appear in this function because it differs from f of 1 in its first decimal, f of 2 in its second, and when you get all the way down, like over here somewhere, it differs from f of n in its nth decimal. So this number can never exist in this table. There are infinitely many of these numbers that cannot exist in this table when you do that way. So like you can subtract 1, and you get 2, 6, 1, 0, 9, right? That number is also not in here for the exact same reasons. And there are, again, infinitely many versions of that in this table. So the importance of that at the time was that there was, the prevailing theory was that all infinite sets had the same cardinality. And through doing this, he proved that that's not the case. There are actually infinitely many sizes of infinity in sets. What that led to in modern application is discrete mathematics, the mathematical field of discrete mathematics. So computer science, or theoretical computer science rather, one-to-one relationships with the set of natural numbers is a denumerable set, proving that the real numbers are uncountable, allowed him to prove that certain sets are countable, and that laid the foundation for all of this stuff, very dear to my heart, the economics things at the bottom here. So that's the whole presentation.
Yeah, thank you. Do you have any questions for her?